Argentatus, the herring gull, weighing a little over in flight by a wing of 2 feet, force exactly equal to its weight. Boeing 747, the jumbo jet, weighing over 700,000 pounds, supported in flight by a wing spanning 195 feet, exerting a lifting force in level flight, which is also exactly equal to its weight. In determining just how an aeroplane flies, and the forces acting on it, its natural behavior and the ways in which we can control it, let us go to the grassroots of aviation. And from a considerable range, take a typical light aeroplane as our example, the Cessna 150 Aerobat. It weighs 1,600 pounds fully loaded and is supported in flight by a wing spanning just over 32.5 feet. This wing, like every other, exerts a lifting force in level flight exactly equal to the weight of the aeroplane. To understand how an aeroplane flies, we need to know something about the air it flies in. What are its properties and how it behaves? This envelope of air that surrounds our planet has certain physical characteristics and patterns of behavior. Though it's invisible, it's made up of molecules like everything else. It has density and pressure, both greatest at sea level, where the pressure averages nearly 15 pounds per square inch. The further from sea level we climb, the lower the pressure becomes. Until at 20,000 feet, it's only about 7 pounds a square inch, and at 60,000 feet, only about 1 pound a square inch. And as the pressure falls, so does the density and the temperature. But that 15 pounds a square inch at sea level is only an average. In fact, the pressure in any given place changes all the time. And as it changes, the air circulates around the areas of high and low pressure, and the wind blows. Now we realize that air is a fluid, seeking its own level like any other fluid. And we can feel the force of its moving molecules as they rush past us and pull at everything in their path. Moving air as a source of energy has been harnessed for centuries with ever-increasing skill and understanding. The aeroplane harnesses the same source of energy by the opposite process, by moving through the air. Let us look at the aeroplane for a moment. It's basically a simple and functional machine. Wings set at right angles to the direction of flight support a body or fuselage to carry the load. Smaller wings and a vertical fin at the tail end of the fuselage provide stability and control. In the nose, an engine and propeller provide the motive power. But it is the wings moving through the air that lift and support the aeroplane. How? To find out, we must first make air visible. We can do this in a smoke tunnel, having first turned it on its side so that we can relate it to horizontal motion. In the tunnel, we can put various solid bodies in the path of the smoke filaments, change their angle to the moving airflow, and see what happens. First, let's take a cylinder. Notice that the airflow curves closely around the frontal curve of its circumference, clinging to it, until suddenly it separates. It can't hold on any longer and becomes unstable and disturbed. It's moving too fast to tuck in behind the cylinder and maintain contact with it, so it has to let go. Now let's take a flat plate. Lying horizontally to the airstream, the flat plate disturbs it hardly at all. But turn the plate across the airflow and see what happens. Turn it back again, and we can see that even at the slightest angle to the horizontal, the airflow over the upper surface tends to break up. Next, a curved plate. This behaves rather better. The airflow is smoother, but it soon breaks away when the plate is rotated through an angle to the airflow. And at a smaller angle, the airflow breaks away underneath, where the plate is concave. But if we look at the wing itself, we find that it's neither a flat plate nor a curved plate, but a combination of the two. It has thickness. The underside is almost flat. The leading edge is blunt and rounded, while the trailing edge is sharp. The upper surface is curved or cambered, and the wing is in fact attached to the fuselage at a slight angle to the horizontal. Cut a section through the wing, and it looks like this. If we set it in the smoke tunnel, we can see how smoothly the air flows around its contours. What's more, we can increase the angle to the airflow by quite a large amount without it breaking away. We call this variable angle to the airflow incidence, or angle of attack. But the really important thing is what happens to the airflow as it flows over and under the wing. Here is the airflow again, this time in slow motion and with an irregular smoke flow. Notice how the smoke accelerates as it moves over the upper surface of the wing, while the smoke flow below the wing tends to slow down. This is just what happens in flight, and it is this phenomenon that causes the wing to lift. For when a fluid in motion increases its velocity, its static pressure, which acts at right angles to the direction of flow, decreases. And when the velocity is reduced, its static pressure increases, so that its total sum of energy always remains the same. To prove it for ourselves, we need another kind of wing model. The surfaces of this one are perforated by a number of pinholes. Each pinhole is connected separately by an airtight tube to a manometer tube. Manometers measure pressure. When we drink through a straw, we suck in to reduce the pressure in the straw, and this causes the liquid to rise up inside it. If we alternately blow and suck on a manometer tube, the same thing happens. And so, if we put the wing section into a wind tunnel, any changes in pressure acting at right angles to the wing surface will be shown on the manometer tubes. Each tube is attached alternately to the upper and lower surfaces. Here is the wing section with wool tufts to show us the airflow. Now let's superimpose it on the manometers and see what happens. The manometers attached to the upper surface rise, indicating a considerable drop in pressure, while those attached to the lower surface fall, indicating a rise in pressure. And it's this difference between the pressures over the upper and lower surfaces that gives the wing its lift. In fact, the pressure pattern looks like this, with the pressure at any given point acting at right angles to the surface at that point. The pressure difference is greatest where the curvature is greatest, least where the surface flattens out. The resultant lift force acts through a point we call the center of pressure, and at right angles to the relative airflow. And so we have a cambered wing flying at a small angle to the horizontal, producing a resultant lift force exactly equal to the weight of the aeroplane in steady level flight. Lift increases with speed. We prove it every time we take off. It also increases with an increase in the angle of attack. Let's follow that takeoff through in the wind tunnel. See how the lift builds up with the speed. In fact, it increases as the square of speed. Then, as we increase the angle of attack at liftoff, there's a sudden, almost muscular increase in lift to help us off the ground. But the extent to which we can increase the angle of attack to the relative airflow is strictly limited. If we increase the angle by more than a certain amount, depending on the type of aeroplane, this happens. The airflow breaks up over the upper surface of the wing, the pressure pattern becomes unstable, lift decreases sharply. The wing has stalled. This can happen at any speed once the wing has reached the critical angle. Thus we can see that the pressure difference that gives us lift can only be maintained if the airflow over the wing remains smooth and undisturbed. The stall can be demonstrated in the air. The angle of attack is increased until it becomes critical. Lift is suddenly reduced. The aeroplane drops, pitching nose down, and quite a lot of height is lost before normal, controlled flight can be resumed. This can only happen when the relative airflow over the wing regains its normal angle and lift is restored. The stall can also occur in level flight. At normal flying speeds, the angle of the wing to the relative airflow can be maintained whether the aeroplane's in level flight, on a descending flight path, or climbing. Always provided that the speed is within normal limits. But if the speed's allowed to decrease in level flight, lift will also decrease. Then, if we try to keep the aeroplane level, it'll begin to sink. When this happens, the relative airflow gradually changes. If the critical angle of attack is reached, the aeroplane will stall and will drop, momentarily out of control. The speed at which the aeroplane stalls will depend on its weight and will increase with altitude as the air becomes less dense. Nevertheless, we must be able to fly slowly, and in particular to land slowly. To achieve this, we can change the characteristics of the wing by fitting trailing edge flaps. These flaps slide out from the wing and curve downwards as they do so. This increases the camber of the wing over part of its span. The upper surface of the wing now has even greater curvature, and the airflow therefore moves even faster, while the obstruction caused by the flap below the wing tends to divert more air over the upper surface, where the pressure is now even lower. In this way, more lift is gained without any increase in flying speed. With the flap fully deployed, lift is still maintained over the wing itself. But behind the flap, the airflow breaks up, slowing the aeroplane down by increasing another force acting on it, the force of drag. This enables us to approach the field at a steeper angle than we otherwise could, which gives the pilot a better view of the landing area, as well as a lower landing speed. is the force that supports the weight of the aeroplane. Lift is generated by moving a precisely shaped and angled wing forwards through the air, causing pressure changes to take place around it. The force that moves the wing through the air is that of thrust. The force that resists its motion is that of drag. Thrust. The principle is that of Newton's third law of motion. To every action, there is an equal and opposite reaction. When we swim, we push water backwards and move forwards in consequence. Action, reaction, equal and opposite. To sustain this balance of action and reaction over greater ranges of speed and endurance, we need more than human muscle. We need mechanical power. To push a boat forwards through the water, we must use an engine-driven propeller to push the water backwards. It's the same with the aeroplane. The jet engine moves the aeroplane forwards by pushing backwards a stream of hot gases with great velocity. The light aeroplane uses a gentler method. An engine-driven propeller pushes air backwards. The aeroplane moves forwards. Action and reaction, equal and opposite. Gathering motion until the airflow over the wing is moving fast enough to lift us off the ground. To create and sustain thrust, the air must be accelerated by the propeller so that it moves faster than the airflow caused by the forward motion of the aeroplane. We can see this in the smoke tunnel with an electrically driven propeller. At rest, the air flows around it. Switch it on, and the air in front of the propeller is drawn in towards the blades and then accelerated backwards at a speed greater than the forward motion of the aeroplane. It sets up a twisting wash in its wake, just like the propeller of a boat, only a lot faster. Thrust can be varied by controlling the power output of the engine. If we increase thrust, we increase speed, but only up to a point. For as speed increases, so does another force acting on the aeroplane, the force of drag. On days like this, we can see drag at work on any highway. Eddying air swirling behind the moving vehicles, wasting their horsepower and their fuel by holding them back, producing a chaotic pressure pattern like this. Drag can be measured. Take a disc of given area and put it in the mouth of an open wind tunnel. Mount the disc on a sprung slide attached to the indicator arm of a calibrated gauge. The airspeed in the tunnel is measured by an airspeed indicator. Notice first that as the speed increases, so does the drag. In fact, the drag increases as the square of speed. With the airspeed indicator steady at 100 miles an hour, the drag on the disc records a value of 5 on the gauge. If we mount a disc double the area of the first, the drag gauge records a value of 10 at the same airspeed, double the drag. Finally, If we mount a disc only half the area of the first and a quarter of the area of the second, we get a reading of only 2.5 at the same airspeed. So the amount of drag depends on both the frontal area of the disc and on the speed of the airflow. However, aeroplanes nowadays can present very large frontal areas to the airflow and somehow manage to fly around at over 600 miles an hour. So there must be an answer. And there is. Streamlining. If we add a bullet-shaped nose to the medium-sized disc, the drag reading at 100 miles an hour is reduced from 5 to just over 1. Add a streamlined tail, and it goes down to less than 1. The drag arising from the shape and size of an aeroplane is known as form drag or normal pressure drag. And if the shape is sufficiently streamlined, the size doesn't matter so much. One obvious way of streamlining an aeroplane is to give it retractable landing gear and eliminate struts. The results of cleaning up the form in this way are often worthwhile, both in terms of performance and fuel economy. But if the gear has to be fixed, then the answer is to streamline it along with the rest of the aeroplane. Another kind of drag that also increases with speed is that of skin friction or surface friction. This is caused by molecules of air clinging to the whole surface area and combining with pressure drag to hold the aeroplane back. We experience both these forms of drag in water. As we move about, we can feel the pressure resisting us. And at the same time, the water molecules in contact with our skin tend to move with us and try to pull the surrounding water along with them. Even when we streamline ourselves and apply thrust, we can still feel the water clinging to us as we move. In a stream of air, it's this clinging layer of molecules in contact with objects in its path that tries to move them and carry them away. If we pour a light, easily flowing liquid over the leading edge of an aeroplane's wing and then take off, we can see that as the aeroplane accelerates, the liquid tends to ripple as the molecules in contact with the surface of the wing try to hold on to those immediately above them. As the outer layers gradually let go, we're left with a thin, slow-moving film of liquid at the surface itself. It's this clinging of the so-called boundary layer to the surfaces of the aeroplane that enables the pressure changes around the wing to give us lift. Pressure changes that also produce drag. Lift and drag are thus inseparable, but the drag component can be reduced, both by clean design and by keeping the aeroplane clean and polished, thus increasing its efficiency. A third source of drag increases in inverse proportion to the speed of the aeroplane, at its greatest when the speed is lowest. We call this induced drag, or trailing vortex drag, and it arises from lift. As a result of the pressure difference between the upper and lower surfaces of the wing, air tends to spill over the wingtips from the area of higher pressure below the wing into that of lower pressure above the wing. The two air streams meeting just above the wingtip form vortices, a corkscrew pattern of twisting air that produces a considerable amount of drag. At whatever speed the aeroplane is flying, however, the sum total of drag is equal to the thrust being exerted by the propeller. Water skis can help us to understand this principle. The skis give us lift and drag. The motorboat provides thrust. When the two are accelerating, thrust will be greater than drag, until drag increases as the square of increasing speed and the two forces become equal. They'll remain in equilibrium for as long as the speed remains constant. Then, as speed is reduced, thrust becomes less than drag, and the balance is lost. On an aeroplane flying in steady, level flight, the total drag force is always equal and opposite to the force of thrust, in just the same way as lift exactly equals weight. After approach, Golf Bravo to Echo Whiskey.
Echo Whiskey, Cranfield approach, go ahead, over.
Echo Whiskey, position Newport Pagnell, 1,000 feet, reach wind limit.
Echo Whiskey, roger, trying downwind left-hand runway 26, Quebec Foxtrot Echo.
In level flight, at steady speed, lift equals weight and thrust equals drag. Lift and weight are about 8 times greater than thrust and drag, but for clarity's sake, we've reduced this ratio in the diagram. So we have two unequal pairs of forces acting at right angles to one another. But suppose we want to climb or descend. What happens to the forces then? As the nose pitches up, the picture changes. 3 of the forces, lift, thrust, and drag, are in the same relationship to the flight path in the climb as they were in level flight. Weight, however, still acts vertically downwards, and so is now at an angle to the flight path, downwards and backwards. It is thus augmenting drag. This directional effect of weight on drag slows the aeroplane down in the climb, so that both lift and aerodynamic drag are reduced. But if we add the drag effect of weight to the remaining aerodynamic drag, the total drag becomes greater than in level flight. To keep the forces in balance, thrust must be increased to balance the new force of drag plus its component of weight. Change from a climb to a descent, and weight, still acting vertically downwards, is now augmenting thrust. The aeroplane will accelerate, lift and drag will increase. So to keep the forces in balance, we must reduce thrust to allow drag to balance the force of weight acting forwards down the flight path. We can experience these forces physically by riding a bicycle up and down a hill. Going uphill, we must increase thrust to balance the proportion of our total weight acting backwards down the hill. If we shed even a small fraction of that weight and deprive it of thrust, we can see what happens to it. Going downhill, the opposite applies. We have to reduce thrust to avoid excessive speed, and the discarded weight will continue forwards down the slope. Once we leave the ground behind, however, no matter where we point the aeroplane, one of the 4 forces acting on it, weight, always acts in one direction, straight down. All the rest of the geometry of flight revolves around that central fact. And so, when we want to climb, we have to offset the effect of weight acting partly backwards down the flight path by increasing thrust, just as we have to pedal harder to ride a bicycle up a hill. When we want to descend without increasing speed, we have to offset the effect of weight acting forwards along the flight path and decrease thrust, just as we have to on a bicycle going downhill. Beyond a certain angle, the descending flight path becomes a glide. There is now enough weight acting forwards along the flight path to keep the forces in balance, and thrust as such is no longer needed. Even in this situation, the forces remain in balance and a steady speed is maintained on the glide path. But the proportion of weight acting forwards along the flight path is now sufficient to act in place of thrust from the propeller and to equal drag. As soon as the aeroplane is leveled out again and power is restored, the four forces resume their normal pattern for steady level flight. In everyday flying, however, the aeroplane has to be maneuverable in all three dimensions. It can be deflected from straight and level flight in the pitching plane around the lateral axis with nose lifting or dropping like this, in the rolling plane with the wing tending to roll the aeroplane around its longitudinal axis, in the yawing plane around the vertical axis, or in any combination of the three. How can this capability be reconciled with a reasonable degree of stability in straight and level flight? Stability is a complex subject, but its basis lies in the plan form of the aeroplane and the arrangement of its flying surfaces. In the pitching and yawing planes, stability is assisted by the tail surfaces exerting leverage along the arm provided by the fuselage. If we look at these tail surfaces, we find a horizontal tail plane and a vertical fin. Let's see how they help stability. To begin with, the four forces seldom act from the same point on the aeroplane. Weight is normally arranged to act from a point ahead of lift, in such a way as to create a nose-down moment around the lateral axis, so that when power is reduced, the aeroplane will pitch nose down. As it does so, the download on the rising tail plane will keep the aeroplane in a stable descent at a stable speed and under normal control. But no matter how stable the aeroplane, the air it flies through is often unstable. Local changes in pressure and temperature cause gusts and currents, which vary the speed and direction of the relative airflow, vertically as well as horizontally. They can thus cause local variations in the angle of attack. When a gust causes a pitch-up moment about the lateral axis, the angle of attack increases momentarily, and so does lift. But inertia, the tendency of an object in motion to keep on going in the same direction, will prevent an immediate change in its flight path. Meanwhile, the tail plane experiences an upload, levers the tail upwards, and slightly overreacts. The aeroplane is now slightly nose down. The tail now reacts in the opposite direction, and through several brief oscillations damps out the disturbance, and the aeroplane returns to level flight. A gust striking at an angle to the flight path can make the aeroplane yaw about the vertical axis, and here the vertical fin comes into play. As it swings out, the airflow provides an opposite reaction to the action of the gust. And once again, oscillations will occur before the fin succeeds in damping out the disturbance. Gusts also disturb the aeroplane around its longitudinal axis by varying the angle of attack as between one wing and the other, and causing it to roll. In this case, the stabilizing influence is the change of incidence affecting the two wings. The wing that is dropping experiences an increase in the angle of attack, and thus an increase in lift. This will stop the roll, but will not level the wings. At this angle, total lift at right angles to the wing is acting slightly in the direction of the roll, while weight acts downwards. through the center of gravity. The aeroplane therefore moves in a side slip in the direction of the roll. In a high-wing aeroplane like this one, the roll and slip is largely corrected by the effect of having the fuselage below the wing, and this will help the pilot to level the wings. In the same situation, a low-wing aeroplane relies more on the angle at which the wings are inclined to the horizontal, known as the angle of dihedral. When the aeroplane rolls, lift increases on the downswinging wing and decreases on the upswinging wing, so the roll stops. Lift is now acting slightly in the direction of the roll, and weight acts downwards. So the aeroplane side slips. Thanks to the dihedral, the relative airflow now strikes the lower wing at an angle of attack greater than that at which it strikes the upper wing, which will be slightly blanketed by the fuselage if the side slip persists. Once again, the pilot must correct the slip and level the wings. No aeroplane is fully stable laterally, and if an involuntary roll of more than a few degrees is left uncorrected, the lift from that powerful wing acting at an angle to the aeroplane's path will pull it into an unstable, descending turn. To recover from it, we must use the controls. The controls of an aeroplane enable us to maneuver it accurately and safely under all normal conditions of flight. Control is achieved by moving hinged surfaces on the trailing edges of the tail and the wingtips, the elevator attached to the tailplane, the rudder to the fin, and the ailerons to the wingtips, all of them operated by the controls in the cabin. Moving the control column backwards and forwards raises and depresses the elevator. Pulling it back raises the elevator, pushing it forwards depresses it. Turning the wheel operates the ailerons at the wingtips. With the wheel to the right-hand aileron is raised and the one on the left depressed, rolling the aeroplane to the right. Turning it in the opposite direction moves the ailerons in the opposite sense and rolls the aeroplane to the left. The rudder is controlled by pedals. Pushing the left-hand pedal swings the rudder to the left. Pushing the right-hand pedal swings it to the right. Each control can be operated separately, or they can all be used in coordination when the maneuver demands it. In the smoke tunnel, we can see how they produce their desired effect by deflecting the airflow. When we depress the elevator, the airflow is deflected downwards, and this increases lift on the tail. When we raise it, the airflow is deflected upwards, and the tail receives a download. The effect is to rotate the aeroplane around its lateral axis. The rudder works in just the same way in the vertical plane, with the airflow deflected to the right or left, so as to push the tail in the opposite direction, swinging the aeroplane around its vertical axis. The ailerons deflect the airflow in the same way, but in opposition to one another, depressing one wingtip and raising the other at the same time, controlling the aeroplane around its longitudinal axis. The remaining primary control is the throttle, which enables the pilot to control thrust. To increase power, the throttle is pushed forward. To reduce power, it is pulled back. Let's see what happens when we use the controls to change the flight path, or simply to take off and climb. The pilot opens the throttle and the aeroplane accelerates. As flying speed is reached, he pulls the control column back, the elevator rises, the tail goes down, the aeroplane lifts off and rotates into the climb. The elevator returns to the neutral position. What the pilot has done is to increase the angle of attack so as to give the wing the extra lift it needs as the aeroplane rotates. Now let's look at the whole sequence in animation. The aeroplane accelerates to flying speed. The four forces are now in play. To rotate the aeroplane, we must put a download on the tailplane by raising the elevator. The angle of attack on the wing increases as the tail goes down, and lift becomes greater than weight. Once established in the climb, the elevator returns to neutral, lift is reduced to balance the component of weight acting at right angles to the flight path, and thrust must be increased to balance aerodynamic drag plus the component of weight acting backwards down the flight path. So the controls are used in this case to change the flight path from level to climbing flight by a controlled increase in lift at rotation. To level off, the elevator is used in the opposite sense, to lift the tail. And thrust must be reduced to allow the aeroplane to remain at a speed where lift exactly equals weight. To descend, the elevator is again depressed, and the tail lifts. And thrust must again be reduced to take account of weight acting forwards down the flight path. At the controls themselves, only very slight movements are required to deflect the control surfaces sufficiently to change the angle of attack and thus increase or decrease the amount of lift from the wings relative to weight, while the throttle is used to maintain the balance of thrust and drag. Going round corners, racing cars depend on their road-holding capabilities to prevent them being hurled outwards off the track by centrifugal force. If we try to turn an aeroplane with rudder alone while keeping the wings level, centrifugal force will cause it to skid sideways. On a bicycle, centrifugal force would throw us off unless we counteract it by leaning inwards towards the center of the turn. And so we bank the bicycle in the direction we want to go. We need turn the handlebars only slightly in the direction of the turn. So it is with the aeroplane. Here it is lift that provides the principal turning force. We've only to bank the aeroplane slightly in the desired direction, and even a small proportion of lift acting towards the center of the turn is powerful enough to pull the aeroplane in that direction. This means that lift has a double role to play in the turn. As we bank into the turn, lift acts partly into the center of the turn to counter centrifugal force and partly vertically upwards to balance weight. The aeroplane turns. If we increase the angle of bank to make a steeper turn, a higher proportion of lift acts towards the center of the turn, and the proportion of lift still acting vertically is no longer enough to balance weight. So we must increase the sum total of lift. First by tightening the turn and so increasing the angle of attack. But this will also increase drag, so to balance it we must increase thrust. Lift and weight are now in balance. And so, to control the aeroplane in the turn, the pilot first applies aileron and a little rudder. In a steep turn, the pilot increases the angle of attack by gradually pulling back on the control column and opening the throttle to increase thrust, so that the vertical component of lift still equals weight. Then when we come out of the turn, we reduce both angle of attack and thrust to their normal values in straight and level flight. We can turn in a glide. Or we can turn in a climb, so long as we use the controls to give the aeroplane the extra lift it needs in the turn. The twin-engined aeroplane differs from the single-engined in several significant ways. The most important aerodynamically is the way in which thrust is usually divided by mounting the engines on the leading edges of the wings on either side of the fuselage. This has the effect of directing the slipstream of each propeller over the wing itself, thus augmenting lift over a considerable proportion of its span.
Echo Whiskey's finals, 3 greens over.
This means that the pilot can use the throttles to accelerate air over part of the wing and thus increase lift, controlling the attitude of the aeroplane in pitch and changing or maintaining height with very little variation in speed.
Echo Whiskey's over.
However, there's always the possibility that an engine may fail. When this happens, total thrust and slipstream are lost on the affected side. Unless we prevent it, the aeroplane will yaw towards the dead engine. And the wing, having lost some of its lift, and now slowing down in the yaw, will drop. To straighten up the aeroplane and restore lift to the affected wing, the pilot must apply rudder against the good engine and hold it there until he can make a safe landing. To do this, he needs help. The way in which a displaced control surface can be held in position against a considerable aerodynamic force is by means of trim tabs. These are auxiliary surfaces fitted to the trailing edge of a main control surface and working in the opposite sense. Thus, a rudder trim tab applied to the right will hold the rudder to the left and vice versa. Trim tabs enable the pilot to correct and hold any normal variation in the trim of the aeroplane without having to hold the control force physically. elevator trim tabs enable the pilot to trim the aeroplane in the pitching plane, and these work in the same way as the rudder tabs. Downwards to raise the elevator, upwards to depress it. These can be used to correct variations in the position of the center of gravity. The total weight of an aeroplane acts through a single point known as the center of gravity. The designer tries to put the center of gravity a little way ahead of the center of lift of the aeroplane so as to give the pilot better control. This is compensated for by fixing the tailplane at a lower angle of incidence than that of the wings, so as to give it a download. But the loading of the aeroplane can change this relationship. An extra load placed behind the center of gravity will move it back to a point only just ahead of the center of lift. The aeroplane will now tend to pitch nose up. So we must trim the elevator to reduce the download and bring the aeroplane back to level flight. The aeroplane can thus maintain level flight despite the fact that the center of gravity is misplaced, provided it's still within the design limits of the aeroplane, and without the pilot having to hold the aeroplane level manually. In the same way, if we need to increase the download on the tail, we can use the trimmer in the opposite sense. The controls give us command of the aeroplane. They allow us to use the forces acting on it, to balance them as we choose, and to control the pressure pattern around the wings as they move through the air, so that we can fly and enjoy the aeroplane to the limits of its performance.